Okay, so we are now in Lecture 2, Part 3, which corresponds mostly to Section 2.3 of your text, and the topic concerns limit laws. So, what are limit laws? Well, some of them are actually theorems, but the book calls them limit laws, so limit laws. And what they are is just a series of formulae which allow us to evaluate limits of certain types of functions. So from your text, I can give you a list of essential ones that we'll be dealing with for the next several chapters. Let me paste them right here. So I would suggest understanding these more than merely memorizing them because they are quite useful when it comes to working more advanced calculus problems. So we have this, the limit laws, and here are the first 6. There are several more, but it begins with this. Suppose that we have a constant c, and that these limits, the limit as x approaches a of f of x, and the limit as x approaches g of x, both of these exist. And I can't stress how important this particular caveat to the limit laws are. Because if any one of these limits does not exist, then these limit laws will not work. So in a nutshell, the first one is that basically stipulates that the limit as x approaches a of the sum of the functions, well, the limit operator, okay, and I circle in red the limit operator, is distributable with respect to the sum, provided that, again, both of these limits exist. The limit operator is also distributable with respect to subtraction. Okay, so that it's an operator that's distributed. See, you take each term in the subtraction, and you distribute the limit operator to each term in the subtraction. All right, now recall that c is a constant, and so the limit as x approaches a of c times a function, well, you can just take the constant out of the limit evaluation. Okay, so you can take the limit operator and associate it with the function, and you don't have to associate it with the constant because, as we said last lecture, I alluded to the fact that the limit as x approaches a of a constant is simply the constant itself. Right, and we more or less showed that last class, or last lecture. Okay, and the limit as x approaches a with respect to a product, again, you can take the limit operator and distribute it term by term. And the limit of a quotient, of course, is the quotient of the limits, provided that the limit in the denominator is not 0. That's more or less common sense, I would assume. And then if n is a positive integer, okay, this is an interesting one. It's a little bit shadowy there. The limit, this is the limit as x approaches a. Okay, and this is in your book. The limit as x approaches a of a function raised to a power, well, you can take the limit operator inside the power operation. Okay, so that's a very useful one. It avoids having to expand this function in into the power to the nth power. You can actually take the limit and then expand the number to the nth power, and that's a lot of work. It's a lot less work, especially if f of x is a complicated function. Okay, let's see. I think I've got a couple more. Let me check. Let's see. Yeah, I believe. And I'll let me see. Let me check. Yeah. Let's see, 6, 7. Yeah, I guess I could go ahead and reuse these. Here are 3 more. Out of the numeric sequence isn't correct, but I think you'll get the point when I paste it here. Yeah, I'll put 8 up in just a second. But again, the limit of here's the rule 7. The limit of a constant is the constant itself, and the limit as x approaches a. This of course is x approaches a. It didn't show up as an arrow. X approaches A of X is just A itself. And the limit of the nth root of X as X approaches A is the nth root of A. Okay, and n again is a positive integer. And there's an assumption here that we're not going to be taking the nth root of a negative number where n is even. Okay, so note this assumption. And let me give you the last one for last two, I think, 9 and 11. Well, 11 got let's see, did I post 11? Let's see, let me check. So, oh, okay. Yeah, so let me write a couple of more here. The limit, let's see, that was 10. Next one should be, oh, okay, yeah, the limit of a power function. The limit as X approaches A of X to the N is equal A to the N. Okay, and again, N is presumed to be a positive integer. Okay, there's another rule. We'll call that rule 9. And then rule 11. Sorry, I'm skipping sequence here. I'm reading them from my notes. So the limit as X approaches A the nth root of f of x. Okay. Now, provided that the limit as x approaches a of f of x exists, okay, then extend the page here. So we have the following caveats for Rule 11. We assume that this limit exists. Okay. We assume it exists and that it's greater than or equal to 0. Okay. And if this is the case, then this limit, well, you can bring the limit operator inside the nth root. So you can just bring it inside. Okay. And of course, again, n is presumed to be a positive integer. All right, so those are the limit laws. All right, so let's work some examples. So let me draw a hypothetical function, or two graphs. Let's see. Let my and this one is from the book, I believe. I'm not sure. Or it may have been a test question. Nevertheless, here we have two functions. F and G are both plotted. So let me accentuate the graph. So F, I'll trace out F because it's hard to see in monochrome. F goes like this. There's a hole at F right here. Here's the this is the origin right there. And then F goes like this. And by the way, there will be a number of WebAssign questions, perhaps test questions, that will be very similar to this problem. Okay, so there's F. Let me accentuate G in red. So G goes like this. It's a linear component here. Then there's a hole right here. And then there's a discontinuity, a jump discontinuity right here. And then it shoots up like this. Okay. And so this would be, and I think we'll presume that this is 1. Yeah, this is 2. This is 3. The origin, -1, -2, -3, and -4. Okay, so there we have it. And so a number of questions pop up, such as, let me write them out. one question is the limit. What is the limit as x approaches 2 of this function, f of x divided by g of x, the rational function f of x over g of x. All right, so what do you have to do? What must be done to evaluate this limit? Well, again, from the theorem from the last class, the left and right limits both must agree, right? And so if we look at 2, I believe I'll take this to be 2. Yeah, and it looks like, well, it looks like, for starters, if the limits, both limits exist, right? So we can, since both limits exist, this would be the limit as x approaches 2 of f of x divided by the limit if, now that's assuming that both limits exist. All right? If both limits exist, then we'll have this result. And so what is the limit as x approaches 2 of f of x? Well, f of x is continuous. F of x exists at 2. So we can surmise that that would be, what, approximately this point? We'll say maybe 1.5. And you can inspect that by going on either side of x equals 2, right? And you'll see that as you approach f of x from either side of 2, the output would be 1.5. But the limit as x approaches 2 of g of x, well, that's another story. That appears to be 0, right? 0. So we'll have 1.5 over 0, which is absurd, right? So this is a does not exist. Even though the limits of the functions exist, it's a DNE. So that limit does not exist. Okay. Something else. Let's see here. How about the limit as x approaches -2, so what do I want? Yeah, of, say, f of x plus 5 times g of x. All right, so let's evaluate this limit. All right, so based on the limit laws, we can take the limit operator and distribute it term by term. So this would equal to the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. All right, and now we can simplify this expression even further. We can factor out the 5, the constant. Okay, so we're applying a number of limit laws here. Plus 5 times the limit as x approaches -2 of g of x. Okay. Now this is predicated on the fact that these two limits exist. All right. So what is the limit as x approaches -2 of f of x? Well, it appears. Okay. So let me circle -2. This is -1. So here's -2, and judging by the graph, it looks like the left approach limit is equal to the right approach. Okay. Even though it converges to a whole, nevertheless, the output was 1. So just reading from the graph, this would be 1. And then we'll have 1 plus 5 times. Now the limit as x approaches, this is a -2. The limit as x approaches -2 of g appears to be -1. Okay, so we'll take that to be minus 1. Okay, and so 1 minus 5 is negative 4. So even though there's a hole here, f of x is not defined at x equals negative 2. Nevertheless, the limit exists. Okay, so what else can we do? Right, how about we ask this one? The limit as x approaches 1 of, say, f of x times g of x, right? So how would we evaluate this, right? So this would equal to by the limit laws, we can distribute the limit operator term by term in the product as if the limits exist. So at the outset, if we assume that the limits exist, then this statement is valid. Okay. Now the limit as x approaches 1, here's 1, if f of x appears to be 2, right? So that would be 2. And the limit as x approaches 1 of g of x. Well, if we approach 1 from this direction, g of x has an output that approaches what? It appears to be negative 2. And if we approach 1 from this direction for g of x, well, the limiting value appears to be negative 1. So in this case, the left limit does not equal to the right limit, so this limit does not exist. So therefore, this limit does not exist. Okay? All right, so that's how you evaluate that limit. All right. Okay, so I'll go ahead and erase all of this and we'll do another one. So let's see here. How about I do this? And the limit as x approaches 2 of, okay, let me put in a different function here. X approaches negative 2 for this function. This would be x cubed plus 2x squared minus 1 and divided by 5 minus 5 minus 3x. Okay, so let's figure out what that limit is. Well, by the limit laws, okay, we can take the limit operator and distribute it term by term. So this would equal to the limit as x approaches negative 2 of the numerator divided by the limit as x approaches negative 2 of the denominator. Okay, this is the quotient limit law. Okay, now let me clue you in on something here. Since the numerator and denominator are both polynomials, there's this technique that I mentioned briefly in class last time called the direct substitution rule, and limits of polynomials can be evaluated merely by plugging in the a value. This is the a value. This is the a value. Just simply plug in the a value into the polynomial, and that will be your limit. Okay, so that's the substitution rule for polynomials. Okay, so this would be negative 8 plus 8 minus 1 divided by 5 plus 6. That would be 11, right? So that would be negative 1/11. Right, so that's the limit. Okay, all right. So we have what's called the direct substitution property. Okay, so next page. So let me write out that. All right, so the direct substitution property. If f is a polynomial or a rational function, and a is in the domain of the function, then the limit as x approaches a of f of x is equal to f of a. Okay, so you can just take the a value and plug it directly into the function and you'll get the limit. All right, and that's true with polynomials and with rational functions, provided that a is in the domain of the rational function. Okay, now, if f is equal to g when x is not equal to a, then the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, provided the limits exist. So let me show you an example of this particular rule. All right, so I'll draw my f and g. Okay, so consider these two graphs for f and g. So f is basically the straight line with a hole at x equals 1. So there's a hole right here. And g is the straight line with a hole, but it's defined at x equals 1 to be 3. So you can see that f and g are not the same functions, but they're equal. The two functions have the same outputs for all values of x except at x equals 1. At x equals 1, f does not exist. At x equals 1, g of x is 3. So in this case, the limit as x approaches 1 for f of x is equal to the limit as x approaches 1 of g of x. Okay, and later on this fact might prove very useful in some very important results. So let's see here. How about we use the limit laws and do a couple of examples. All right. So how about the limit as t approaches, I'm sorry, not t, h, make that h. H approaches 0 of this function. Let me type in the function. So we'll say 3 plus h squared minus 3 divided by h. Let's see. Ah, where did it go? Try it again. The limit as h approaches 0 of 3 plus h quantity squared minus 9, excuse me, minus 9 divided by h. All right, so what is that limit? Okay, so now this is an interesting problem. Clearly, if you attempt to use the limit laws, your g of x function is h, and the limit for your denominator would be 0, and you would think this would be does not exist. But there is a caveat. If when you use the direct substitution property, you can use the direct substitution. Well, you cannot use the direct substitution property because 0 is not in the domain. Right here, it violates this condition that a is an element of the domain. Okay, so 0 is not an element of the domain of the function. Since 0 is not in the domain, if supposing for a moment that we use direct substitution and we plugged in 0, we would have, and then evaluated the resulting rational function, we would have 0 over 0 by direct substitution. Now, whenever you have a 0 over 0 case, after direct substitution, I'm going to put it in quotes, direct substitution yields this absurd result. That means this is an indicator that actually, in fact, this limit does exist, because this is what's called an indeterminate form. And we'll talk more about those in chapter 4, but whenever after direct substitution you have a 0 over 0, you have an indeterminate form. And when you have an indeterminate form that results after direct substitution, then, in fact, the limit does exist, right? And it can be solved for. And the way we could demonstrate that is we can go ahead and simplify the numerator. And so the numerator is 9 plus 6h plus h squared minus 9 divided by h. Okay, and that is equal to the limit as h approaches 0 of 6 plus h. Okay, and that is equal to 6. So the limit does exist. I may have a limit calculator. Let me check. I'm checking the class website. For a limit calculator. Let's see, checking. Yes, there is a limit calculator. So let me pull that up in Smart Notebook. So let's pull up another page. I'm trying to find the limit calculator. Here it is. It's this one. Yeah. So this is on the class website. So instead of writing it in terms of h, so how about we write our function here, which would be 3 plus x squared minus 9. Okay, so instead of h, I'm going to write it in terms of x. Okay, divided by x. All right, and so the limit as x goes to what? 0, right? And we hopefully will get 6 as an output. And sure enough, we do. And it looks like they plotted the graph, which is almost a straight line. So yeah, so you can actually work some of these limit problems on using the calculators on the class website. Okay, so let's see here. Let me reiterate another theorem from last class, just as a reminder, because we'll need this again and again. What do I have here? Okay, so we know the limit as x approaches a of a function is a number if the left and right limits are the same. Okay, so this I can't emphasize this enough. Okay, the importance of this theorem. Okay, so the limit as x approaches a of f of x is equal to L if and only if the left limit is equal to L as well as the right limit. Okay, so we have to have those two very important results. Okay, so let's do some examples. How about the limit as x approaches 0 of the absolute value function? All right, so maybe perhaps we can solve that using a graphical approach. Sorry, my home PC's internet's a bit slow. All right, so let's say y is equal to the absolute value of x. Okay, and here's the graph, and so the question is the limit as x approaches 0 of the absolute value of x. Let's see, do I have an absolute value? I'm not seeing it. I'm sure it's out there. Interesting, we don't have it in the algebra section. Well, we'll just write absolute value of x. Okay, so we want to find this limit. And we'll just do it graphically. We'll just do a trace. So as we approach 0 from the left, observe the outputs, the ordinates of the points that are displayed in the box. It goes to 0 from the left. How about from the right? Probably we anticipate the same thing, okay? And so it goes to 0 as well. Okay, right there at 0. So this limit is equal to 0. Okay, so absolute value. How about this function? The absolute value of x divided by x. Okay. So we want to evaluate the limit as x approaches 0 of this function. So over x. Okay, so what is that? And its graph is shown in red. Okay, so there's the graph. So as we approach 0 from, say, the left, okay, where do our outputs go to? Well, it looks like from the left, our outputs go to -1. And of course, when we have x equals 0, of course, it's undefined, right? Oh, by the way, this is an example of an indeterminate form. A 0 over 0 case, which does not resolve into a limit, and the reason is because of the absolute value, of course. Okay, so the previous disclosure I made, where when you use direct substitution and it resolves into an indeterminate form of 0 over 0, you would expect a numeric output. Well, this is one example where an indeterminate form evaluation does not yield a numeric output, and these types of functions are comparatively rare. Okay, these forms. Okay, so of course, as x approaches 0 from the left, the output is -1, and as x approaches 0 from the right, the output is 1. So the left limit and the right limits are not the same. So the takeaway is that this does not exist. And the way we can deal with this is we can replace absolute value of x, okay, with its definition. We reformat the rational function okay, as into one without absolute value, right? So this would equal to 1 if x is greater than 0. And so in this case, really the absolute value of x over x is in fact not a rational function, but a piecewise defined function. So the rule still holds about indeterminate forms. In fact, this is not an indeterminate form. It's the function is, technically speaking, a piecewise defined function. Okay, so there's no dilemma here. What other kinds of functions can we deal with? Oh, okay. So how about, let me erase this. And let me get rid of this limit problem here. And define a function piecewise, say y is equal to square root. Can I write that? Yeah, square root of x minus 4 for x greater than 4. Okay. And y is equal to 8 minus 2x for x less than 4. Okay, and y is not defined. Where is my graph? Zoom in, zoom out. Hello? I'm not seeing my graph. Why did it not draw my graph? Oh, this calculator has issues. Try it again. Okay, so we have y is equal to 8 minus 2x for x less than 4. Okay, does that not show up? Why is the graph tool stopped working? Oh, that's too bad. Okay, no worries. I have it sketched out. Can I draw y equals x? I'm not sure why my calculator stopped working. Oh, there we go. Maybe the zoom wasn't there. Okay, let me try it again. So y is equal to 8 minus 2x. Okay, so there's 8 minus 2x for x less than 4. All right. So there we, okay, so there's the red portion, and then I just had a zoom problem. Okay, so y is equal to the square root of x minus 4 for x, of course, greater than 4. All right. So here's a piecewise defined function, and the function is not defined at x equals 4. So technically speaking, see right there, at x equals 4, the function is undefined. There's a hole. So let me kind of annotate a hole at x equals 4 for emphasis. So there's a hole right there. And so the question is, what is the limit as x approaches 4 of this function f of x, which is this piecewise defined function? Okay, so all of this, these two branches, this is my f of x. All right, well, we can ascertain this graphically. So as we walk along, observe the ordinates. Okay, and so at x equals 4, as we get closer and closer to x equals 4, notice that the output gets smaller and smaller. It goes to 0, at least as we approach x in this direction. Okay, so as we approach x from the left, that is, the output approaches 0. All right, now how about as we approach 4 from the right? Where does our output go to? So in this case, again, the output gets smaller and smaller, and it goes to 0 as well. Okay, so this limit does exist. So here's a case where the limit of a piecewise defined function exists. And so we'll say that is 0. Even though the piecewise defined function is not defined at x equals 4, its limit is equal to 0. Okay, all right. Okay, so the next function, I'm not sure if I'm able to draw it. Let me try using this graphing calculator. I don't think it'll work, but I'll give it a go. And this is the greatest int function, okay? So is there a help? Let me see if the help allows it. Let's check the help and see if it'll do it. Tools, resources, greatest. Can I type here? Well, let me type. It's not letting me type. Greatest integer graph. It doesn't let me. Okay, well, let's try. Let's see if we can. Y is equal to, it's typically written as this. I'm not recognizing it. Okay, let's see, functions. Inverse calculus, miscellaneous. Let's check miscellaneous. Zero Flora and then max mod is, nope, I'm not seeing it there. No, I don't think this tool supports the greatest int function. Okay, no worries. That's fine. Just so happens that I do have a graph for the greatest int function. So let me go ahead and post it right here. So let's talk about that. Yeah, let me grab hold of the image. And this is another important function in calculus. Okay, so let's talk about it. Okay, so the greatest integer function is written like this. Okay, so we say y is equal. Actually, it's just one little symbol. So we say y is equal to greatest integer of x, and its graph will look like this. Okay, so let me fill in the details. Let's use a blue pen for it. Okay, so it's often called the stair-step function, and I'm accentuating it here. Oh, another symbol for the greatest int function are these two little bars right here. Okay, so you might see it written that way in web assign. And we'll do some for values of x, outputs for values of x less than 0. So it's basically a sequence of line segments that have holes at the right endpoints of the line segments. Okay, so what greatest int means is this. If you pick a number, any number x, pick any number for x on the x-axis, all it means is that the greatest integer function is the number, not the number, is the integer, the first integer to the left of x, if x is not an integer. Okay, if x is an integer, then the greatest integer of x is x itself. All right. So for instance, say if I pick 2.9. Okay, so 2.9 is right here. X equals 2.9 and the output is here. So the first integer that to the left of 2.9, I'm sorry, that's not 2.9, that's 1.9. 2.9 is here. So the first integer that's to the left of 2.9 is 2. So greatest integer of 2.9, well, what is the first integer to the left of 2.9? That's just 2. Okay? The greatest integer of 2.0001, well, that's 2. Okay? So the greatest integer of 2 is just 2. Okay? The greatest integer of 3.1 is 3. Okay? Because 3 is the first integer that's to the left of 3.1. So how about the greatest integer of -4.8? Okay. Well, what is the first integer that's to the left of negative 4.8? Well, that's negative 5. Okay. To the left. The first integer that's to the left. Not to the right. It's not 4, but it's negative 5. Okay, so that's greatest ends of negative numbers trip up a lot of people. Remember, it's just the first integer that you encounter when it's to the left of x. All right, so with that in mind, what is the limit? Let's ask the question, what is the limit as x approaches 3 of the greatest integer function? All right, so the limit as x approaches 3 of greatest in x. Okay, so let's look at the graph. So as we approach 3 from the left, okay, as we approach 3 from the left, what is the output? The output is 2. Okay, so we can write that down. The limit as x approaches 3 from the left of greatest int is equal to 2. All right, so how about as we approach 3, okay, as we approach 3 from the right, from this direction, right? So the limit as x approaches 3 from the right of greatest int, okay, that would equal to 3. And so those two limits are not the same. So the limit as x approaches 3 of the greatest int function does not exist because the left and right limits don't agree. And you can extend this concept to say that the limit as x approaches any integer of the greatest integer function does not exist. So the greatest integer function, the limits for greatest integer functions only exist at non-integers. So a rather peculiar result. All right, so I want to introduce a theorem. They'll also be useful when we talk about derivatives coming up in a couple of lectures. Actually, I want to talk about a couple of theorems. So let me grab hold of those. Okay. And with respect to limits and inequalities. Limits and inequalities. So what are the ramifications of those? Okay, so here we go. All right, so if f is greater than g when x is near a, except possibly at a, and the limits of both f and g exist as x approaches a, then we can say that the limit as x approaches a of f of x will be less than the limit as x approaches a of g of x. Okay, so this is a very important result. Okay, so we can actually order limits based on the ordering of the functions. Okay, and I'll show you an example of that, how that's useful in just a second. So if we combine this very powerful theorem with another theorem, which we've already mentioned, called the squeeze theorem. So let me post that up as well. So we have the squeeze theorem, which we talked about in the limit as x approaches 0 of sine x over x in one of the lectures. So we have this so-called squeeze theorem. Okay, and the squeeze theorem is if we have an ordered relation of 3 functions, f is less than g, which is less than h, when x is near a, except possibly at a, then, also, we also have another condition. If the limit as x approaches a of f of x, okay, if the limit for f of x is equal to the limit for h of x, then the limit also holds for g of x. See, g of x is wedged between two identical limits, then g of x must have the same limit. That is very important as well, and we'll use that quite a bit in Chapter 3. I also have an illustration I can show you which exemplifies those. So let me grab an illustration here. Where was it? See if it's on this. No, it's not on this page. Cancel. Not paint. So an example of an application of the squeeze theorem would be this. So consider, let's see, g, function g, which I'll draw, accentuate in blue. Okay, so there's function g. And, oops, is that G? No, that's not what I meant for G. Sorry, let me erase that. That's not my G. My G goes like, how about I choose it to be this? Yeah, G has to be in the middle according to the squeeze theorem, right? So I'm going to put G right in the middle between F and H, right? Okay. Okay, and then I'm going to accentuate F as colored, say, orange. Let's make F orange, okay. So here's my F. And then I'll make H a green color. Nice colors, right? Okay, so in this case we have f of x is less than or equal to g of x, which is less than h of x, near x equals a. So we have this ordered relation near x equals a. All right, now, and also what's demonstrated in this drawing is that the limit as x approaches a for f of x is also equal to the limit as x approaches a for h of x, okay? So the two limits are the same. And then since g is wedged in between f and g, say on this number line, where a is an element of this interval, okay, then we can say that g of x attains the same limit, which is this number right here, L. Okay, so there's an example of how you could visualize the squeeze theorem with three different functions. So let's do a more tangible example. Let's consider another limit problem. Let me go back to the web page. Do I still have my calculator up? Yes, I do. Okay. More or less, right? Okay. So the problem we're going to do now as an application of the squeeze theorem and the limit laws with inequalities is I want to find this limit. The limit as x approaches 0 of x squared times sine of 1 over x. Okay, so I want to find that limit. Now, we can't use the product limit laws, right? Because in doing so, obviously we can't divide by 0. So the limit laws do not work here because the limit of this factor does not exist. All right? So we can analyze the function graphically. Okay, so let's go ahead and graph it. Y is equal to x squared times sine of 1 over x. Okay, and we want to look at what happens as x approaches 0. Okay, so let's zoom in. Okay, so it looks like it flattens out. Okay, so it looks like it's going to be 0, but how do we know it's 0? It's hard to determine graphically that it's 0. So what I can do is we can say, well, let's graph y equals x squared. Okay, right, and then let's also graph y equals negative x squared. And for those of you who've had trigonometry, you'll know that x squared and negative x squared are constitutes the envelope for the graph y equals x squared times sine 1 over x. Okay, so this is actually an important concept from trigonometry. Now let's zoom in real close. Around 0 because zoom out a bit, get some perspective here. And what I'm trying to illustrate with this particular graph is that x squared okay, well we know that it's rather obvious. It's kind of, well, maybe not so obvious, but we can kind of guess that the sine 1 over x right here, what is the range of the sine function? Well, we know that sine 1 over x is going to be between -1 and 1 because that's the range of the sine function, as long as x is not 0. Okay. All right. So for all allowed values, but we're not concerned about the value of the function at 0. Remember, we're just concerned with the limit as x approaches 0. So as we get close to 0, but not at 0, even though this function is not defined at 0. Okay, so from that perspective, we can take this inequality and we can multiply through by x squared. Since x squared is a positive number. Okay, so we get this interesting relationship. All right, so this is legal. Now, what would happen if we took the limit as x approaches 0 for this inequality? Well, if we did that, we could use direct substitution. So the limit as x approaches 0, let me go ahead and write it out for you. So based on the theorem from the previous slide, we can take the limit operator and distribute it term by term in the inequality as well. Okay. So I have this result. All right, and so we can go so this is equal to the limit as x approaches 0 of negative x squared, and that's less than the limit. Now, remember, we cannot use the limit laws in evaluating the limit of this peculiar function, okay? But just because we can't use the limit laws doesn't mean that the limit doesn't exist. The limit may very well exist. We just don't know yet. But here's the proof that it does exist. The squeeze theorem will demonstrate that. Okay, the limit as x approaches 0 of x squared, right? Okay. Now, we can use direct substitution for this limit. Okay, so that's 0 is less than the limit as x approaches 0 of x squared sine 1 over x, which is less than 0. Okay, and so there's a squeeze theorem. Okay, so if the limit is greater than 0 and less than 0 at the same time, then the limit must be 0. So therefore, this is equal to 0 by the squeeze theorem. Okay, so interesting result. All right, so that is it for lecture 2, number 3. The next lecture, we'll talk about the definition of a limit, and that may be somewhat complex, but we'll have a lot of problems to solve with this. So we're still not ready for the project development yet, but after the next lecture, after the completion of the next lecture, which might take 1 or 2 class periods, you should be ready to handle your second project. Okay, so that'll be it for this particular lecture.